So good afternoon. It's my pleasure to welcome you to the second talk of this numerical analysis session. And the second speaker of this afternoon is Professor Siddhartha Mishra. And he's going to talk about all the convergence of numerical schemes for hyperbolic systems of conservation laws. Please, Professor.
Thank you very much. And also, thanks for getting my name correct, more or less. At the outset, I would like to thank the program committee and the panel, which selected me to be invited for this talk, and I'm really honored by that invitation. So I'll talk about systems of conservation laws. So these are nonlinear systems of PDEs of this generic form here. Cap U is the vector of unknowns. Cap F is what is called the flux function. And as a prototypical example, I present the Euler equations of gas dynamics, which are written here. Rho is the density, U is the velocity field, P is the pressure, and E is the total energy. And they represent the conservation of mass, of momentum, and of energy. So these are the prototypical examples. There are many other interesting examples, and you already saw some in the previous talks in this session. So even though this is a very large class of equations, what unites them are two features. First is, of course, hyperbolicity, which refers to the finite speed of information propagation. And second is the role of the nonlinearity. And as many of you are aware of, what the nonlinearity does is that even if you have smooth initial data, because of self-steepening, in finite time, you get the formation of what are called shock waves. So these are the things that really unite this rather disparate class of equations. Now, because they are so useful or so important in applications, numerical analysis or the design of numerical methods for systems of conservation laws is fairly mature. The pioneering contributions started in the 50s and 60s, and I've listed some of the real pioneers in the field. Arguably, today, the most popular framework is the so-called finite volume scheme. And I'm just presenting a cartoon to explain what it is in one space dimension. So this is space, this is time, and the quantity of interest, the object of interest that you evolve are the cell averages. And these are well defined even if your function is discontinuous. And what a finite volume scheme does is discrete conservation. So it says that the rate of change of cell averages is given in terms of the balance of fluxes. So the fluxes measure how much stuff is coming in and how much stuff is getting out at each interface. And to calculate these fluxes, we can follow Godunov and remember or observe that the cell average at each interface, at the beginning of a time step, you have what is called a Riemann problem, piecewise constant states. We can solve this either exactly or approximately very efficiently. Some examples are here. These waves propagate, and at the next time step, we re-average them, and then we get a finite volume scheme. Since we are just using piecewise constant basis functions, we have a first order scheme. To get high order in space, we need to work with piecewise polynomial reconstructions. However, remember that the underlying function is discontinuous. So in order to use piecewise polynomials, we need some sort of a non-oscillatory reconstruction procedure. A variety of these are available. Some of them are listed here. And the end result is a system of ODEs, which is written here. And in particular, you can evolve them by using what are called strong stability-preserving Runge-Kutta methods. So this package of finite volume schemes, approximate Riemann solvers, non-oscillatory reconstructions, and time stepping, strong stability-preserving time stepping, is extremely successful in practice. I'll just give you some examples from my own research. So with this, you can, for instance, simulate what are called magnetic towers instabilities in the core collapse of a supernova. You can simulate the propagation of Alfvén waves in the solar chromosphere. So these are some Alfvén waves which are propagating there. In geophysics, you can simulate tsunamis. Manuel Castro already referred to that. In particular, the so-called Lituya Bay mega tsunami. And you can even do uncertainty quantification. For instance, by the multi-level Monte Carlo method that Mike Giles spoke about on Friday, you can do climate science, in particular large eddy simulation for stratocumulus clouds. So this is an observed cloud field. And with some of these schemes that I just described to you, you can reproduce them fairly accurately. And the classical examples are, of course, flows past aerofoils. So these are just some glimpses from my own work. So you can imagine how successful this is from the whole community. So that brings me to the fundamental question of numerical analysis, which is that of convergence. So if I label all my mesh parameters by delta and call the numerical solution as U delta, the question is what happens as delta goes to 0? Does U delta converge? If it does so, in what topology? And what does this limit satisfy? How does this satisfy the equation? This is a fair question to ask. The first candidate for this limit are entropy solutions. Remember that we have shocks, so we can't work with classical notion of solutions. We integrate with the test function, multiply with the test function, integrate by parts, and we arrive at the definition of a weak solution. However, weak solutions are not unique, and we need some additional conditions. They're called entropy conditions. They come from second law of thermodynamics, generalizations of that, and you require that also in the sense of distributions. So this object is called an entropy solution, and we hope that as delta goes to 0, U delta will converge to an entropy solution. Is that true? So it is true for scalar conservation laws when you have exactly one unknown. There are varieties of papers on that. If you have first order schemes, then you can use some control on the derivative in the functions of bounded variation. If you have high order schemes, you need more sophisticated techniques, for instance, compensated compactness or H measures. Nevertheless, as long as you have a scalar conservation law, even if you have several space dimensions, unstructured grids, you have convergence. However, for the real problems, multidimensional systems, the ones that I just showed you, convergence is an open question. And because of that, to sort of test our schemes, we use some sort of empirical demonstration of convergence or benchmarking. What do I mean by that? I give you an example. So I choose a scheme, in particular these schemes that I derived some years back with Fjordholm and with Eitan Tadmor, who is in the audience. So these schemes have some desirable properties. They are entropy stable. They satisfy a discrete version of the entropy inequality, and they are also very high order accurate. I choose my equation, the two-dimensional Euler equations, periodic boundary conditions, and initial data that corresponds to the radial version of the short shock tube, which Shi Jin spoke about in his lecture. So these are on 3 different meshes, 128 squared, 256 squared, 512 squared. And when I take successive differences between successive resolutions, you see that there is some very neat convergence in L1. So the hope is that this translates into a wider class of problems. So by benchmarking on examples like this, I go to compute real problems, and this is an example. This is the computation of the atmosphere of an exoplanet in my group. And the point about this computation is that at each time step, we have 10 billion degrees of freedom. This is a very, very big calculation. And to go from a calculation like this, where things work, to something like this is a bit of a leap of faith, right? The question is, we do it, but is this leap of faith justified? And that's why I asked the question, what are we computing? Let me try to investigate that a little further by taking another example in 2D. So the same scheme, the same box, periodic box, so periodic boundary conditions. All that I change, the same equations, all that I change is the initial datum. So this is the so-called Kelvin-Helmholtz problem. So you have density, you have a difference in density, and at each interface you have a shear. So because of that, I'll test it on a sequence of grids. So this is on 128 squared. Because of the shear, you get the formation of these big vortices. And at 256 squared, you get more vortices. 512 squared, you get further structure. At 1024 squared, even more structure. And we compute the finest resolution that we can afford, which in this case was 16,384 squared, a very, very finely resolved computation. And you can see how fine structures and how much of mixing is taking place. Needless to say, each time I'm refining, I'm getting more structure. So when I take these successive differences in L1, you see that there is a flat line all the way down to 16,384 squared. So clearly, experimentally, this does not converge compared to what we saw before. There are some caveats. One can argue that this is very, very slow convergence. But in that case, it's useless, because if it does not converge by 16,000 squared mesh points, it will never converge. One can say that this is a very specific example. It is not the case. As soon as your flow becomes unstable or turbulent, this happens. In particular, it will happen here. And what is even more intriguing, it will also happen in this example. I've stopped the shocks here, but if I would have let them go on, and because of periodic boundary conditions, they would have come back, and they would have given the same sort of instability and lack of convergence. And the last point here is that this is just one numerical method. However, if you do any reasonable numerical method for conservation laws, you'll get similar qualitative behavior. So there will be no convergence. So this brings me back to entropy solutions. Remember that I want to understand what is my limit for numerical methods. There are theoretical problems with entropy solutions. In particular, we know that they are not unique, thanks to Dillele, Sekelhidi, and others who showed that there are so-called wild solutions. I just showed you or tried to convince you that numerical methods may not converge to them. So based on these criteria, it is fair to assume that we need a different framework, different notion of solutions. And the question is, can the numerical evidence hint at what sort of framework we are going to get? It turns out that it can. And again, if we come back to this example, so now what I'm going to do is instead of a single calculation, I'm going to randomize it. In particular, I'll take very, very tiny perturbations of this interface, and I'll try to compute the whole ensemble. Let's try to do that. So it takes a bit of time to load. So remember that if I had a single realization, a single example, I had no convergence. When I take two of these tiny, tiny perturbations and average them, there's some averaging, but there is no convergence. When I take 8 of them, I start seeing some of the small structure being averaged out, but still there is no convergence. When I take 64, you start seeing that the fine structure has been averaged out, and you start seeing some convergence. And when I take 1024 of these realizations, you start getting even better convergence, proper convergence here. So the numerical evidence says that even if your deterministic realizations, what I call samples, have bad behavior, statistical quantities are much better behaved. In particular, they converge. So this is known to people doing fluid dynamics. It's known to people doing chaotic dynamical systems. The question is, how do I incorporate them and formalize them? How do I put them into a mathematical framework? And this brings me to the second candidate that I have for the convergence of numerical methods, which was our first attempt to understand a mathematical framework to incorporate statistical quantities. It's called entropy measure-valued solutions. This goes to DiPerna in the 1980s. Other people also contributed. Let me explain it in terms of this picture. So the classical or the weak notion of solutions is you fix time, so these are snapshots. You fix a point in space, almost every point, and you get a unique value of your observable, density, pressure, and so on. But in a measure-valued solution, at each point in space, what you have is not one value, but a whole spread of values and a probability distribution which tells you how likely a certain value is. At a different point, you have a different probability distribution. So when I say Young measures, think of probability density functions at each point. So this is, of course, it can happen that at every point you have exactly one value. In that case, your probability density function, a measure, collapses onto a Dirac measure, and you're back into your classical notion of solutions, a weak notion of solutions. So once you have this picture of Young measures, one can interpret the solutions of conservation laws simply by integrating with respect to the measure. You can also interpret the entropy condition by integrating with respect to the entropy function. And this was already done by DiPerna 35 years back. So our contribution is we have devised an efficient algorithm to compute these entropy measure-valued solutions. This was done a few years back. The paper only appeared last year, but it was done a few years back by Fjørholm, Keppeli, myself, and Ethan Tudmore. And I want to spend some time on this algorithm because this is vital for what I'm going to talk later. So the idea is you want to compute a measure, and it's difficult to compute a measure. So what we do is that there is a correspondence between measures and random fields. So there's a theorem which tells me that if I take a measure, there's always a random field whose law is this measure. Once I have that, I can sample out of this random field. So these are different realizations, essentially Monte Carlo samples. Once you fix each sample, you can evolve them, for instance, by a numerical method of your choice, and then you can assemble them together. Once they're evolved, you can assemble them together by what is called an empirical measure. So this is nothing but a Monte Carlo approximation of your ensemble. And this object here is a Young measure. And for me, this is going to be a candidate for my entropy measure valued solution. The question is, does it converge? As delta goes to 0, you refine the mesh, and as the number of Monte Carlo samples goes to infinity. But the idea is very simple: random fields, sampling, and some sort of a Monte Carlo approximation. It turns out that it does converge if your numerical method satisfies a discrete entropy inequality, and it satisfies something called a weak BV bound. So there is not the derivatives in this problem, they will always blow up. Means there is no control on the derivatives in any strong sense. Instead, what we have is a rate at which the derivative blows up. So this is written here in one dimension. If you have some control on the rate at which it blows up, together with the entropy inequality, one can actually prove that as you refine and take more samples, these approximations, they will converge in the right topology. I'll talk about that in a second, to an entropy measure valued solution of the system. And the topology is a weak star convergence, weak star topology on Young measures. So essentially, just in words, what converges are not just functionals. Functionals are space-time averages. They don't converge necessarily, but statistics of functionals of interest, they are the objects that are going to converge. So you have to do some ensemble averaging in addition to space-time averaging, and these objects are going to converge. Just in case you think that this is a very weak notion of convergence, whenever you make measurements, this is exactly what you measure. You measure functionals, like the temperature in the room, and you measure statistics of that. There is always error with the measurements. So what we see is that all one-point statistical quantities will converge according to this theorem. Does that work in practice? We return back to this favorite example that I have, no convergence for each sample. But as soon as you take the mean, I fix the number of samples, and you can see that there is convergence as I refine my mesh. It converges rather nicely. If you take the variance, and variance tells you even more information than the mean in these problems, those objects also converge very nicely. And then I choose, remember that the Young measure is nothing but a PDF, a probability density function. So I fix a particular point, and I compute the probability density function with resolution. So this is 128 squared, 256 squared, 512 squared, 1024 squared. You can see that there is some very nice convergence even of these quantities. So in contrast to the deterministic case, in contrast to entropy solutions, remember space-time averaging, with ensemble averaging, what we have is that these are limits of numerical methods, and as a consequence, we have global existence, even in multi-space dimensions. Another important fact or observation, numerical observation, is what is written here. So I again compute these point probability density functions. So in the beginning, I had very, very little uncertainty. So your initial Young measure was almost a Dirac. And because of the evolution, because of the chaotic evolution, what has happened is that this PDF or this measure actually spreads out. So what we are computing is, even if you start with a function, your solution, your measure-valued solution, will be a genuine measure. So this will mean that it will be very difficult to have a theory for conservation laws using only functions, because the computations show that you have to deal with measures. So all is well and good, and this is a nice object, but there is a caveat, and the caveat is non-uniqueness. So measure-valued solutions are a rather weak concept of solutions, and they're generically non-unique. What do I mean by that? I'll just give you an example. So Burger's equation, the simplest possible conservation law, that nonlinear conservation law that you can think of. My initial data is a non-atomic Young measure. So I just fix a point, and this is my initial data. This is the same initial data, the same terminal condition. However, and this is not a numerical calculation, these are analytical calculations. I've just plotted what is formula. Then you can see that in one case, there is just shock going through the system, and this measure simply flips. It moves to the other measure. In another case, it's a gradual transfer of measure. It moves one by one. but eventually you arrive at the same measure. So these are two bona fide entropy measure valued solutions, analytical, and this shows that you cannot have uniqueness. Generically, they are going to be non-unique. However, what we compute with our numerical methods are super stable. Just to illustrate that, I do different perturbations for my initial datum, and in the phase, in the amplitude, with the uniform, and with normal distributions, you can see that modulo numerical error, I get the same solution. Similarly, even if I take different numerical methods, so one is this techno schemes, the other is a completely different class of schemes. In both cases, I'm computing the same numerical methods, so same numerical solution. This tells me that the computed measure valued solution is much more stable than something that is a generic one. So there are some additional criteria that it has to satisfy, and what exactly are these additional criteria is the rest of my talk. So in order to discover this additional criteria, we go back to the drawing board and we go back to the definition of measure valued solutions just for a scalar conservation law in one space dimension. Let me recall. So the definition of a measure valued solution is you have an evolution equation for the mean. Okay, of course it's not closed, it's for the mean. And you have a bound for the second moment because S, the entropy function, is a convex function, so it's essentially quadratic. Now what I'm asking is, I have some constraint on the mean, I have some constraint on the second moment, and I want to determine a whole measure. Now, anyone doing textbooks, elementary statistics knows that that's not true. I can always change the higher moments of a measure without changing its mean and second moment. So this simply is not enough to specify a whole measure. On the other hand, if I had a test function, smooth large class of test functions, and if I tried eta, and if I tried to constrain all these test functions, then I can determine a measure uniquely. Let's try to do that. So we have an evolution equation. Things work out except for one particular term, which I've highlighted in red. This term tells me that I need information about the statistics I'm integrating with respect to a probability measure at the point x and at the point x plus h nearby. So this precisely is what is a correlation. So what do I mean? Again, in terms of pictures, in order to determine the Young measure uniquely, I need information about conditional probabilities or correlations, at least at nearby points. So this is necessary, and this is the reason why measure-valued solutions are not unique, because there's no information about correlations. So now I can play the game. Okay, fine, I specify these 2-point correlations. Then I can go back to the drawing board, repeat a calculation like this for 2-point correlations. Because of the nonlinearity, what I'm going to get is that then I need information about 3-point correlations. To specify this uniquely, I need 3-point correlations. To specify 3-point correlations uniquely, I need 4-point correlations, and so on and so forth. The bottom line is I need all possible multi-point correlations in order to have some chance of uniqueness. One can be brave and try to do that, and this was done a couple of years back with Fjorholm and Lanthaler. And we introduced a class of objects which we call correlation measures. These are nothing but formalizing correlations. So the idea is that each of these objects is a Young measure that is defined on tensor product spaces. Now we necessarily have to use tensor product spaces, takes values in probability measures on tensor product phase spaces, lots of technical conditions, but just think of it as correlations. So this is the law of the measure corresponding to the law of correlations. There are some assumptions. Consistency means that this is a hierarchy. So if I know the 10th member of this family, I know the previous 9. If I know the 50th, I know the previous 49, and so on. So that's why it's a hierarchy. Then I have a technical condition on what happens nearby. So I need to somehow relate the correlations at small scales. This gives rise to some sort of a Lebesgue differentiation theorem for these objects, and we call this condition as diagonal continuity. So these objects are well defined, and they're there, but there are infinitely many. They're a family of objects. The first surprise to us, perhaps, was that actually these objects, they are completely equivalent to an object that is well known in stochastic analysis. And that object is probability measures on a LP space, probability measures on a function space. Now let me try to explain this pictorially because that's easier. So what I'm saying is, remember that we have 1-point PDFs, 2-point correlations, 3-point correlations, 4-point correlations, and so on. This entire family is completely equivalent to a probability measure, but on functions. What do I mean by that? So I have just drawn a bunch of functions here. So what you can do is that you can give a certain weight to the green function, to the blue function, to the orange function, and so on, non-negative weight, so that this adds up to 1. So this is a probability measure on functions. As I said, it's a well-known concept in stochastic analysis, and it's completely equivalent to these correlation measures that I just wrote down. In fact, it's a localization of these correlation measures. Moreover, and this is a bit surprising, that it is completely, all that you need to determine this measure on an infinite dimensional space are a countable family of moments which are written here. So now, in order to determine the solutions, I come to the third candidate for my convergence of numerical methods, something that I call statistical solutions. So these are time parameterized probability measures on a function space. The analogs for Navier-Stokes were done some years, 30 years back. And the idea is that you have to evolve the moments. Remember that the moments tell you exactly what this measure is going to be. It turns out that one can actually write down evolution equations for the moments just by multiplying things, because we are only interested in tensor products. Things are somehow linear in tensor products. So you can write down these kind of equations, product equations. I don't go into the details. You can interpret them in terms of measures, and you arrive at statistical solutions. So for a system of conservation law, it's a map, measurable, weak star measurable, from time to probability measures on LP, such that, remember that these probability measures on a function space are completely equivalent to this finite dimensional correlation measures, whole family of it, such that it satisfies these kind of tensorial equations in the sense of distributions. So I have an infinite family, but each member of the family, it takes values in a finite dimensional space, increasing finite dimensional space. Those who know statistical physics, the mu t, the measure on a probability, infinite dimensional probability space, would have satisfied what is called a Liouville equation. This family, on the other hand, satisfies what is called a BBJKY hierarchy. So this is the sort of equivalence. It appears a very esoteric abstract object. How is it related to the solution concepts that we have seen so far? It turns out that it is not abstract at all. It's rather concrete. Let me try to justify that. So first, if you assume that your initial data and your solution is a Dirac measure concentrated on an LP function, then this statistical solution is nothing but a weak solution. So as soon as you take a Dirac, or coming back to this picture, if it only took value 1 on one of these functions and 0 everywhere else, a Dirac measure, you're back to the classical notion of solutions. So it's just an extension of classical notion of solutions. Second, the first member of this family is a Young measure. It's just 1-point PDF. And because it's a multiplication, it has one term. So you recover the definition of a measure-valued solution a la Di Perna. So a statistical solution is nothing but a measure-valued solution plus information about correlations, but not just any correlation, all possible multi-point correlations. So you have the measure-valued solution, which we had computed already, and you keep on adding more and more information to the measure-valued solution. So this object is much more rigid, it's much more tight, and it has a lot more structure to it. So that's why it's much stronger than a measure-valued solution, and we can actually compute it. So that's the connection between the convergence of numerical methods. It turns out that the same algorithm that I use to compute measure-valued solutions actually computes a statistical solution. Let me walk you through that. So remember that I have an initial measure. Now it's a probability measure on LP. There are ways in which I can sample out of it. So what I do is that I take Monte Carlo samples essentially. If for each of these samples, this is a function, use your favorite numerical method. This gives you an approximate solution. Club them together by the so-called empirical measure. And this object here is a probability measure on LP and will be a candidate for my measure-valued solution. So the algorithm itself is very simple. So sample, evolve the samples, average them. This is ensemble averaging. The question is, in what topology does it converge, and if it converges at all? The topology will be a very natural topology on probability measures, the so-called weak topology, but on probability measures on an infinite dimensional space. However, we need some sufficient conditions to check convergence for numerical methods, and these are provided here. So first, I need a uniform bound in LP, and then the structure functions, which tell me correlation at small scales. I need some uniform control on that. If you have these sufficient conditions in a forthcoming paper, by using some rather heavy analysis a la Ambrosio, we show that this sequence will converge in the weak topology to a probability measure on LP. The question is now, for a numerical method, you have to test these conditions, these sufficient conditions. This can be done in another forthcoming paper. As long as your numerical method satisfies the discrete entropy inequality, then automatically the first condition is satisfied. It belongs to a probability measure. Then remember that I had this weak PV bound. What this weak PV bound does is that gives me some control on oscillations at the scale of the mesh. So the structure function at the scale of the mesh behaves in a certain manner. But however, this is not sufficient. I have information at the smallest scale. I have information at the large scales. It doesn't matter what happens at the large scales. What really matters is what happens at intermediate scales, because this is what will determine this uniformity. There I need an additional assumption, which is very natural in the context of turbulent flows. I say that there is some approximate scaling of structure functions. If that happens, then this uniform diagonal continuity is satisfied. And I can prove with some effort a Lax-Wendroff theorem, which tells me that these approximations that I constructed from ensemble averaging, they actually converge in the weak topology to a statistical solution. So here there is a convergence theorem, and what converges are all possible multi-point statistics. So mean converges, the variance, the point PDFs, structure functions, objects like this, which measure correlations at small scales. The Fourier transform, which is given by the spectrum, multi-point correlation functions, all these objects are going to converge. So this is a very peculiar situation. So you may not have any convergence of any deterministic quantities. However, all statistical quantities that you can write down, they are going to converge. And there is a theorem which tells you that. Let's test this out with some numerical examples. So this is again the same problem. We had convergence of the mean and the variance. What we can do is we can do better. We can put some metric. These are measure spaces, so you can't put norms. You can put some metric, and a natural metric is on the weak topology is the Wasserstein metric. We heard a lot about that, optimal mass transport. So convergence in the weak topology, which we have, implies convergence in the Wasserstein metric on probability measures on LP, which in turn implies convergence in some natural topology on Young measures. And this is the natural topology in Young measures, is Wasserstein metric on phase space and LP on the physical space. There it nicely converges, as you can see. So these are all one-point statistics. If you have a picture like this, it means that every one-point statistical quantity will automatically converge. Two-point statistics, these are the structure functions. They also converge very nicely. What is more, this Wasserstein metric on two correlation measures, there is very neat convergence on that, observed convergence on that. So this means that all two-point statistical quantities are going to converge in this case. So verifying the theory. Here's another example. I take the Euler equations, but now I take constant density, constant pressure. I take Brownian motion as my initial data for the velocity, uncorrelated Brownian motion. We want to compute the structure function in this case. This can be done, and it very nicely converges, as the theory says. And also in this Wasserstein metric, pseudo-Wasserstein metric on Young measures, you have very, very neat convergence. This is like really linear convergence. You can't expect better than that. We have done some three-dimensional calculations, preliminary ones. So this is the same problem, but in three space dimensions. You're looking on the side. So this is a single sample, 128 cubed, 256 cubed, more vertical structures, 512 cubed, 1024 cubed. You keep on getting more and more structure. So on the other hand, if you look at the mean at 128 cubed, looks much nicer. 256 cubed, you can verify this convergence. The higher statistics are still not ready, so higher resolutions. Variance at 128 cubed looks nice, and 256 cubed, you can see that there is some convergence already. We have not finished the computations. So in sort of summary, I still have a few things to say. Statistical solutions, you can understand them and you can compute them, and this is what the talk has been so far. However, there are many, many open questions. From a theoretical perspective, the key questions are, remember that I had the scaling assumption. To have a complete theory, I need to either relax it or I need to prove it. So far, it seems that relaxing it by using some new numerical diffusion operators seems to be more promising. The big issue is, of course, uniqueness and stability. And here we have some results for scalar conservation laws and also some weak, strong uniqueness results for systems, again, based on some deep optimal mass transport theory. However, we are nowhere near complete here. Right? This is the challenge. Our numerical results show that there is tremendous amount of stability for the computed solutions. So there are some additional criteria that we are computing, and we need to find them. And this is what we are doing now, trying to search for suitable selection principles. But since this is also the session on scientific computing, in the last 10 minutes that I have, I'll try to focus on the computational challenge of computing these solutions. Many of you know that Monte Carlo is a very expensive method because of the slow convergence rate, and 3D simulations are anyway very expensive. Just to give you some idea of numbers, so this is a single 3D simulation at 1024 cubed, so one of these calculations, this one. And we have a very optimal code for it, which I have developed now for 10 years or so, very scalable and so on. We have a very powerful computer. This is the most powerful computer in Europe, Pisdaint in Switzerland. And on this, for a single simulation, it required 38,000 node hours. So 38,000 processors working for 1 hour for a single sample. So if I need to do 100 samples, no one is going to give me that kind of computational time. So in order to manage these kind of computations, I need a speed up of a factor of 1,000. This was the calculation, this was the challenge that I have set myself and my PhD students, that we need to get a factor of 1,000. The first thing we did, one of the reasons why this was so expensive is because modern supercomputing architectures, they're primarily based on GPUs. So GPUs are the ones that give them the high numbers, and the CPU code will never do well on them. So we changed it to a complete multi-GPU code, very efficient. It's called Alsvin, named after a figure in Norse mythology. And then we computed on the same system. Now for a single resolution, single run, we got it down from 38,000 to 1,200. So just by changing it took 1 year. This is hard work. But we got a factor of 33, a factor of 30. Remember, the challenge is a factor of 1,000. I already have a factor of 30 just by going to hardware, but that's it. We are not going to get big leaps in hardware. So we need to do something at the level of algorithms. One possibility is to use multi-level Monte Carlo. Mike Giles spoke about that extensively. Just to recall, the idea is that you do a few samples on your fine resolution meshes, a very large number of samples on coarse resolutions. Now, this program has worked very well in our research group in Zurich for many hyperbolic problems, tsunamis, flows past aerofoils. Sometimes we get a factor of 1,000 speed up over Monte Carlo. If we did it in this case, our problem is solved, right? Because we had a factor of 1,000. But unfortunately, that's not going to happen. This picture tells you why. So it turns out that for multi-level Monte Carlo to work, this details the difference in successive resolution. This has to decay. Here it's actually constant, so there is no gain. However, we know that our observables are space-time averaged. So when we do time averaging, we see that the variance of these details, they are a factor of 5 less than the variance of the actual solution. So from multi-level Monte Carlo, we can get a factor of 5 to 10, let's say a factor of 5 to 10. But I need a factor of 30 to 40, and 5 to 10 is a long way there. So it does help. Not as much as we wanted, but it still does. Another option would be to do quasi-Monte Carlo. So quasi-Monte Carlo is a better integration rule. This is just a picture. It's better distributed. So you can see that in almost every box, you have quasi-Monte Carlo points, whereas Monte Carlo is much more randomly distributed. We have tried quasi-Monte Carlo. This did not give us the sort of gains that we wanted because we don't have enough regularity, but nevertheless, it gave a factor of 2 to 3. And this again, I take it, right? So together with these two things, you still get a factor of 10, 12 or something. I need a factor of about 30, 40. So there's still a factor of 5 to 10 missing. So now if you do computational science, this day the big thing is machine learning, in particular deep learning. There's a plenary talk tomorrow on this topic, and the last few months I've been working on it, and the idea is to replace your computations with neural networks. And when we do that, on model problems, like the one-dimensional short shock tube, I get a factor of 20. And the hope is that for these realistic problems, I will get a factor of 5, and that's enough, right? Because if I get a factor of 5 from deep learning, I can combine them in an ingenious manner with multi-level Monte Carlo, from which I get a factor of 10, and I get a factor of 30 from hardware, then my problem is solved. But this is still a question mark. Maybe in a couple of years, this will be answered. So I'm almost at the end of my time, so I go back to my fundamental question that was there always in the bottom panel. What exactly are we computing with numerical methods? The answer to that may be nothing, right? Because with plain numerical methods, you might not compute anything. However, if I rephrase the question by asking, what are we computing with ensemble average numerical methods, then for sure we are computing entropy measure-valued solutions. This is a theorem. With some additional hypothesis, we are computing a much more rigid object, tighter object, statistical solutions. We are computing that. But we are actually computing, because of stability, what we observe, we are computing something which is even tighter than that. And this is the thing that I don't know yet. And to find this out will probably give us some idea about some new numerical methods that might be necessary to compute there. But we are here. One needs to go somewhere there. And there are some related topics that I did not touch upon. There's a parallel program in my research group about doing the same things for incompressible flows. Similar considerations apply. And uncertainty quantification, this is a natural framework for uncertainty quantification, actually parameter-free uncertainty quantification. And it's also a basis for Bayesian inversion, means you don't know this initial probability measure exactly, you don't know it at all, you want to calculate it from data, and you need to do some sort of inversion, Bayesian inversion, to get that. And these are all actively pursued research topics at the moment. So with that, my time is up, or it's almost up, so I will stop here, and thank you very much for your attention.
Thank you, Professor Mishra, for the nice talk. So the session now is open for questions and remarks. Since I'm the chair, allow me the first question of all. You mentioned a few slides ago about the neural network and improving the effects with 20.
Yeah.
So how can you be sure that this is the best that you can get?
No, this is by far not the best we can get. By far not, because this is very preliminary work. I'm just training a few parameters. I'm sure that in some other applications I get a factor of 500, but I've just put the most conservative number that I got at the moment. This is by no means, you might get much better numbers, right? But a factor of 20, I'll be very happy. That's so these are very preliminary work, right? So I think I train like 50 parameters or something. Today you can train 10 million, so there is hope. Yeah. So there is hope that you can do much better.
I mean, you start out with a more or less deterministic model, and you do all the statistics and whatnot. So how does the neural network come into that? I mean, for me, that's still something where you don't have an a priori model and...
No, neural network is a calculational, it's just a way to compute. It has nothing to do with the intrinsic model. So it turns out that this is actually a numerical method for the Burgers equation. And what you can do is that, well, this is a very poor, it's just a cartoon, So I have several functions, square, because it's Burgers equation, max, abs, identity, products. All these functions, they can be approximated by neural networks. Neural networks has nothing to do with the theory. They're just a way to calculate things fast. So in that way, it has nothing to do, you can't use a neural network without any a priori knowledge of your model to get these kind of rich dynamics. However, that's not what I'm saying. What I'm saying is that I have numerical, this is why I said it's a consistent neural network. It's a numerical method written as a neural network with some undetermined parameters that are trained on the data to get better answers. But by no means am I saying that you can plug in a neural network and get a solution as complicated as this one. That's probably not going to happen. Or maybe it can, I don't know. But so it's a calculational aid. It's not by any means sort of the actual model.
So if this is not the case, let's thank the speaker again.
Thank you very much.